All right, let's go ahead and take a look at P.1. So P.1 is a section that is further in the back of the textbook and it deals with probability. It's when we go through this lesson, it's going to most remind you of what we did in section 2.1, which was when we were doing the categorical variables with the fractions, like the proportions, numerator, denominator. And so it's going to feel a lot like that. Now, as far as probability, it is trying to tell you the likelihood of something happening where as far as like as low as or as high as we can go is 0 and 1. And if we split the difference between those, if something we say has a probability of like zero point 0.5, like right in the middle, that is to say that there's like a 50% chance it's going to happen. So maybe, maybe won't. Anything less than that, right? Anything that has a probability of below zero point 0.5 has a lower chance or less than chance of happening. Anything above zero point 0.5 is more likely to happen. And then we've got our cutoffs. Like the lowest probability you can ever have is 0. The highest you can ever have is 1. And whenever we say that there's a 1, the probability of 1, which is like 100% chance it's going to happen, that just means it's definitely going to happen. 0 would mean nope, it's definitely not going to happen. But for all the problems that we're going to be doing, it'll be some decimal between 0 and 1. Now, just to get us started, again, like I said, it's going to be a lot like section 2.1, where we had numerator, denominator, proportions, fractions, which we could then turn into decimals. And an example that can at least just kind of get us started is this idea of like the 52 cards that are in a standard deck. When we think about all 52 cards, there are several different types. There are some cards that have a 2 on them, some that have a 3, all the way up to like 10. Then you got Jack, Queen, and King, which are your face cards. And then you got your 4 aces. But then a further way to think about the 52 cards is that there's 13 of them that are hearts, 13 diamonds. Then you got your clubs and spades that are your black cards. So like half are red, half are black. And the whole idea is that if suppose we were like to shuffle them up and just randomly like select one card, one of the questions we could ask is what's the probability that it's going to be a black card? So you've always got to think of the total number that are possible. There's 52 total cards, but as far as specifically narrowing down those that are black, you've got 26. And again, that's because there's 13 clubs, 13 spades. Now, as a decimal, which is what we'll do quite often, is the version that we're going to be looking at. Now, we're going to start off with the fraction, switch it to a decimal. So there's a 50-50 chance that you could get something that's black, something that's red. Then if we think about like the probability of getting an ace, well, in terms of aces, there's only 4 of them. So there would be a 4 out of 52 probability that you could get an ace, which is a lot harder to do as opposed to getting a black. But go ahead and put that in your calculator, see what decimal you get. And again, anything that's below 50% is less likely to have happen. You should get 0.77. And so if they say which of those two events is less likely to happen, drawing an ace, there's only about a point, about a 7, 8-ish kind of percent chance that that's going to happen. Now, one other idea that's going to come up is not the probability of something happening, but the probability it doesn't happen. So, you've seen like the Weather Channel, they might say, there's a 30% chance of rain. So 30% of those like in the viewing area are going to get rain. 70% are not, you know, going to maybe see rain. So That's like the idea of a compliment. You might get rain, you might not get rain, but it's always 100% something's going to happen. And so the little formula that you do is one minus it does happen to get the probability it doesn't. So if you're ever looking for something not happening, then what you'll do is just subtract it from 100. So in this little example two here, suppose the probability of some event happening, they're just calling it B. The probability that event B happens is zero point 0.3. Probability that it doesn't happen, well, we would just subtract that from 100 and you get 0.7. So 30% chance it will happen, 70% chance it won't. So just be looking out for this word. It will pop up sometimes where it's not that they want it to happen, it's that they don't want it to happen. In this case, it would be probability of getting a diamond. So the way you could do it is first calculate the probability that you do get a diamond and then subtract that from one. Like just get rid of all the diamonds. So in this one, what it would look like is, well, first of all, we've got there being a diamond. So you would do one minus probability there's a diamond. And if you're not familiar with the cards, it's helpful to come look back up here. There's 13 diamonds. There'll be one minus 13 out of 52. But notice that 13 out of 52, if you put that in your calculator, that's 25%. In other words, a fourth of the cards are diamonds, three-fourths are not diamonds, but that would be the probability that you don't get a diamond. So just kick out all the diamonds. Now, what we're going to be doing in this section is a lot of times like leveraging one of these. This little table that you see here is a two-way table. And again, two-way tables, we've seen these before. It's because there's two different categories. One category, excuse me, two different categorical variables. This is about hockey, and so one the more specifically the hockey Hall of Fame, like the best of the best players. And so one of the categorical variables is the country, right? Whether the player originated from Canada or whether they were more of a USA player or Europe or just other. And then the other categorical variable is the position that they played. Like were they an offensive player, defense, or were they goalie? And you can see definitely Canada has a whole lot of players who have been inducted into the Hockey Hall of Fame. And what we're going to do is use this table as a way to find probabilities. Again, it's all about fractions. If you look at A, it's asking to find the probability. And so you imagine these just like the cards. Like you're going to mix up all the hockey players and notice that there's 251 of them. Mix them all up and then just pull just one of them out by random. And that would be 251. What's the probability that you happen to pick somebody who plays offense? So you've got, let's see, where's our offense right here? There's 138 who play offense out of the 251. Would be 138 over 251. And then you'll put that into your calculator. And you'll need to round, right? Either to two, three decimal places. This one, if we were to round to three decimal places, it would end up being 0.550. But that extra zero at the end, you don't absolutely need that. You can take it off if you want. You got about a 55% chance of selecting somebody who belonged to the offensive position. Now, the other thing is, well, oh, here, let's do one. They want probability that they're not Canadian. So there's a lot of Canadians. So what's the probability you don't get a Canadian? I think probably the most straightforward way to do this one is just to go and add up everybody who's not Canadian. In other words, put all your other countries together. There's 10, 11, and 3. So 24 out of the 251. And then go and divide that. Now, for these homeworks, I'll go and say it now. You do not, if the homework, and I think I tried to take most of them off where it would say, you have to show work. A lot of this stuff is like small little calculator things where, I mean, if you don't show me that in the homework, like I think that's going to be fine. It's not a bad idea, but you might consider just going ahead and getting into the habit of doing the fraction and the decimal, because on the test usually I do ask for both. Right, give me evidence of like what fraction you use to get your decimal answer. I just recommend probably just going in and just doing it both all the time, so whenever it is asked of that you do both, you're already kind of used to it. Now the the next few examples, it's all about the language. More specifically, they're going to use words like or, and, if. And I'm going to start with the and, like this one here. Like, suppose we mixed up all the players. What's the probability that they happen to be both of these things? Right. And that's the word that we're going to put right here in the notes. Anytime that they use the word and, it has to be someone who fits into both of those categories, that they were a European and they were a defenseman, European and defenseman. So here's all your European. Here's all your defensemen. And so one way you could think about it is you're looking for the intersection. So notice what's at the crisscross of these two little ovals that I did. There's 3. Yeah, there's only 3 players amongst all these 251 players who happen to just be both of those things, European and they play defense. And I've got it right here in the notes. Yeah, it's all about finding the intersection, someone who belongs to both of the groups. So you would do your 3 out of 251. You would do your division to get your decimal version. I usually don't see students have too much issue with the ends, whenever the word end is the key word, but I do sometimes see some issues whenever the word is or. So let me real quick stress, like, what do we mean by or? You're going to take your USA people, right? That they're USA or goalie, and you're going to add them all up. Anybody who belongs to USA plus anybody who was a goalie, you're going to add them all up. But you need to be careful with this one because there are going to be an overlap. So whenever you count some of the USA people, you might also at the same time be simultaneously counting some who are goalies. So you don't want to accidentally double count those. Whenever you count a part of USA, don't also recount them again with goalie. Watch, let's do this. So we're trying to find someone who's USA or goalie. So if I were to just do this, oh yeah, here's all the USA people. That's 7 plus 2 plus 1. And then if I were to go, okay, let me also add all the goalie people. Well, that's them right there. That'd be the 33, the 1, the 2, the 0. Well, the 1 we already counted whenever we were counting the USA people. So you don't need that extra 1 2 times. So one way you could think about this is we're just going to do it the 7, the 2, the 1, and then just also the 3, the 2, the 33, the 2, and the 0. And then that's it. So if you accidentally did this by just doing it this way, well, let me add up all the USA people and let me add up all the goalies. Oh, it's 46. You would actually be wrong by 1 because that would accidentally be counting that 1 twice. I think probably the safest way is the way I did it just a moment ago. Just add up your USA people and then just add up anybody who you haven't already counted that's in the other column. Now, if you add all the up, 7 plus 2 plus 1 plus 33 plus 2 plus 0, you're going to get 45. Now, it's again, it's really important that whenever you're doing your homework to consider uh, that you check the answer key. I mean, there's an answer key there, so you can immediately assess yourself and make sure that all your work is accurate before you plug it you submit your work. So if there was someone who maybe had been doing this when it had been like a homework problem and they accidentally got 46, they'd be like, wait, why did I get 46? It's like, oh, because I accidentally double counted something twice. Um, and I'll put the note up there, as we get 179 for our final answer. Uh, for the second bullet point here, it's just that whenever you're doing an or, you're trying to take anybody who's in the first group or in the second group or in both groups. Just be sure do not double count. Yeah. Now, so far, I want you to notice that we've used the denominator has been 251, 251, 251, 251. You're thinking, oh, I guess it's always going to be 251, 251. And nope, there are also sometimes where it's considered a conditional probability. And what that means is that they're going to say, well, we only want to focus on a specific row or a specific column. And so that's going to be the word if. The word if is meant to trigger just a column or a row total rather than the whole entire like big grand total. Now, as I mentioned, that word if is the word that you have to focus in on. Like if what? And so if we look at this next one, part E, it says if an inductee is Canadian, they only want you to focus on the Canadians. So we go up to the two-way table. For now, they don't want us to be looking at anything else. They just want us only to focus on the row Canadians, which would be 227 Canadians. That's going to be our denominator. And then if you read the rest of part E, it says that they play goalie. So it would end up being those two numbers I just circled. There was 33 goalies out of the Canadians, if that's all that we're specifically focusing on, just the Canadians. So that if is going to tell you to focus in on just a certain row or just a certain column. And again, we'll go ahead and do our usual calculate, get the decimal. But before I spoil it, go ahead and read part F and for yourself see where that word if, who does the if belong to? It should say if this. Sometimes I have students who, when they read this, they think, "Oh, I think the if is supposed to go with Canadian," but it's not. Saying what is the probability that an inductee is from Canada if they play offense? Now, you're never ever actually required to do what I'm doing here, which is write it out in words. But sometimes when I work with students who have maybe felt like they're sometimes putting the wrong numbers backwards or using the incorrect total altogether, if offense is our denominator. And if you look up at the two-way table, that's going to be a specific column. And then once we do have that column, we're going to get those that are Canadian. So watch, let's go up there and let's find the offense. Yeah, so that very last question that we're doing here doesn't want you to look at anything else. It just wants you to look at of those that play offense, how many happen to be Canadian? And it's 128 out of 138. But when I put this lecture together, I was trying to find, a variety of situations, and that right there just about that covers it. Might be the big total, it might be just a total from a certain column or a certain row. You would go ahead and divide to get your, yeah. So of all those that played Canadian, who were offensive players, like 80, almost 89, uh, close to 90% of them were from Canada. Now, there's actually not too much more with this lesson. I can start saying that there's really just the last main thing is that sometimes they're going to be selecting two back to back, like sequentially. So in the first few pages of this lesson, it was all about just selecting one, like selecting one hockey player or selecting one card, and that was it. But now this one is they want two things to happen, like back to back. And whenever you're doing probability of something happening followed by something else happening, you multiply the probabilities. So it's called the multiplicative rule. Now, let me go ahead and just jump right into an example. So an example four, it's just reusing the idea of the deck of cards. So if you had all the deck of cards and they asked for what's the probability that you get a king, and then after the king, you get a queen. So it'd be, and again, you're not required on your homework to write this little notation, probability queen, king times probability queen. I mean, it doesn't hurt, but if we're doing this, getting a king first, well, remember, there's only four of every type of card. So there's four kings and there's four queens. So it would be 4 out of 52 times 4 out of 52. You put that in your calculator and you would get your decimal answer. Now, the reason why that one was the exact same proportion probability both times 4 out of 52, 4 out of 52 is one of the key things that they said is that after having selected the king, they did return it back to the deck. So whenever they went to go grab the queen, the whole 52 cards were all there. But B is different. You're gonna select a card, but then whenever you select that card, you're not gonna put it back. And they say it right here. You keep the first card. So when this one is looked at, it's a scenario where they want to select, first of all, select an ace and then get another ace. So whenever you go get the first ace, all of them are there, 4 out of 52, but then they don't put it back. They keep it. So when you go grab the second ace, two things are affected. One is you don't have all 52 cards there. You're missing one of them. And then in this scenario, because they're doing the same card again, like if they were trying to select the king, then you would have all four kings there. But now one of the aces has been selected, it's gone. So when you reach back into the deck, there's only three aces. So in other words, this example is one where both the numerator and the denominator are affected because the first one was never returned. Again, you would put this into your calculator. Go ahead and give it a shot. Yeah, put 4 over 52 times 3 out of 51 um, and round. Yeah. Now, I'm not going to have any questions about, were these dependent, independent, but I do want to at least mention it here while it's new and it's fresh. The first scenario with the queen and the king, those would be considered independent. I'm not even going to write it, but if you want, you can write, right here. This part A was an independent situation, and what all that means is that that the first selection was not affected in any way by the first selection because they put the king back. But this one here would be described as being dependent. Like what happened with the second selection was influenced by the first selection because they didn't put it back. So it affected it. Again, I don't. I'm not going to have any questions like, was this dependent, independent? Just know if you happen to be reading the book or maybe doing extra problems or maybe another YouTube video or something, and they talk about dependent, independent. Independent is whenever the first pick and the second pick didn't have any impact on each other. Now let's try another example here where two pieces are being selected or two of something are being selected. This is about candies, Reese's Pieces, and they tell you that um, in a bag of Reese's, there's 28 that are orange, 15 yellow, and 12 that are brown, and there's 55 total pieces. And then now they're just going to give us a few different questions about probability. First of all, if you reach into all 55 of the pieces when they're all there, what's the probability that it's not brown? And kind of with working with students, I think usually the most typical way to do this problem is just to add up the other colors. You've got your yellows and you've got your oranges. You would add those together. Yeah, add up your yellows and your oranges, which would get you, what's that? 43. Yeah, that would be the not. I mean, the other way you could have done it is done, 55, take away the browns, take away the 12 browns to get 43, but this one's done. Now B and C are going back to the idea that, maybe things get replaced, maybe things don't get replaced. It's going to be two fractions being multiplied because they're selecting one piece followed by a second piece. Now, you're more than welcome to go ahead and pause the video and see if you can find what's the fraction times what fraction if they want to pick a yellow and then an orange one, and they do put it back whenever after the first selection. And then also maybe try again, pause the video and try this last one here where it's, they want to pick an orange and they want to pick another orange one, but they keep it. They don't put it back. How would that affect the numbers following in the second probability? All right, so I'm gonna let you just pause the video. I'll be quiet for a little bit and then we'll do this one. Okay, so maybe you've tried this one. Again, it was to try to get a yellow, which would be 15 out of 55. They put it back, so that means you've got all 55 pieces available again. And now this time it's a different color. It's orange, which there's 28 of those. And again, you just go ahead and multiply that together. And the other problems, I mean, it's very similar in that you're picking two pieces. They want this to be orange, orange. So when you do the initial orange, there's 28 oranges out of 55, but now they don't put it back. They keep it. So one orange is missing when you go get the second piece. So immediately that's going to drop you down to 54. And at the same time, you're missing an orange because it never got put back. And these would be the two fractions that you could put into your calculator, get your decimal. I'm going to go ahead and do these. It'd be 0.139 and 0.255. Again, for the homework, it's, I'm not going to be checking to see whether you did the fraction. Mainly, I'm looking for like the decimal. But when you get to the quizzes and the tests, I've learned that it's usually to my benefit and to the student's benefit to just go ahead and write the fraction. That way, in case you do have something a little bit off, I can always look back and give you guidance on, either you had the wrong denominator or you had the wrong numerator. So let me see if something does go off track. I can try to get you back on track with a little bit of feedback. All right, let's go ahead and end this one. Um, on this one, they're doing left-handed. So again, they're assuming that if someone's left-handed, then the only other option is someone being right-handed. Um, they've got it broken down by gender. They say that 11% of males are. Let me get my pen back. There it is. 11% of male are left-handed, and that 9% of females are left-handed, which would mean the rest of the males and the rest of the females are right-handed. And that's all that we're going to be doing here is just working primarily with those two numbers. If we were only doing that, we wanted to pick just a female and she was not left-handed, well, we would need, some students say like the opposite, but it would be that we need the complement of 0.09. So if there's 0.09 that are left-handed females, then 1 minus 0.09 would give us how many females are right-handed. So 91%. Now B and C are going back to the multiplicative rule. They want you to pick two things back to back. And the very first thing would be that they want a male who is left-handed, and then they want a female immediately after that who is also left-handed. So in that case, all it really is that they want you to multiply both of those two together. A left-handed male followed by a left-handed female. So 0.11 times 0.09. You'll get 0.099. And then C, I think probably the best way to describe what C is about, we just did lefty times lefty. And now what C is doing is it wants you to do a righty times a righty. And so the way they say it is you want one male who is not left-handed, and then you want a female who is also not left-handed. So you want a righty times a righty. So what you'll have to do is 1 minus the complement for males. All right, that would be 11% of males are left-handed. So 0.89% of males are right-handed. And then you'd also do this one we did already for part A, is that if 9% of females are left-handed, then that would mean 91% of females are right-handed. And this is what they want. They want a right-handed male followed by a right-handed female. There's an 80 or almost like an 81% chance of that happening. Now this one doesn't need any stat key. That actually is the end of the P.1 probability. So I'll go ahead and end the recording there, but if any questions come up, let me know. Take care.